Hello and welcome in this presentation, which is topic 7. We would like to discuss an application of generalized functional observers to realize a stack feedback control law, which is a more general stack feedback control law. It has a delay linear combination of the delay stack vector in here. And we will show that to realize this feedback control law, we can design a generalized functional observer to directly realizing this control law. And therefore, based on this approach, we can have a similar observer-based control scheme that will give us lesser hardware components. That means in terms of the components like integrators, proportional gains, summers, and also on. And also it will give us better transient responses. And so this is part of the chapter, which is chapter 14 in our book. Before I go on with this presentation, if you recall that in the last presentation where we look at the estimation of an unknown input for a time delay system, and we discuss a third order observer without internal delay. And somehow when I did the simulation, it didn't give me the figures that are expected. And so here is the simulation codings of that example again, where we estimate a known input using a third order observer without an internal delay. And so I like to cut and paste the coding and put it into MATLAB. And we should get a figure as expected. The figure that we expected is this figure here, where we have a much quicker settling time, in other words, conversion time. So that's the figure itself. Okay, and it just shows that the observer, third order observer, give us a quicker conversion time compared to a second order observer with an internal delay. So now we like to discuss a very interesting application of generalized functional observers. Now you can recall that in the previous talks we discussed the design of generalized functional observers to estimate generalized functionals of a class of time delay systems where we could have this delay present in the stack in the output measurement vector, or without that in the output measurement vector. And now we like to show an application for it. And the main message that we like to discuss here, to say here, is that based on directly estimating this control law, without first estimate this entire stack vector, and then realize this term, and then delay it, and then realize this term to realize this control law. Because as you know, the stack vector might not be available for feedback control. And that's why we implement an observer. Now, if we do that way, that's the one possible way. Or we can estimate this generalized function, this functional first, and then estimate this functional first, and then delay it, or something like along the way. But again, these options will not give us a simple observer by control scheme compared to directly estimating this control law using a generalized functional observer. And so the discussion here is directly based on this chapter, which is in application. Okay. we apply whatever we done in chapter 13 to the problem, to solve the problem of design observer based controller, and sometimes it is called dynamic output feedback controller. So what we have here is a standard time delay system with a constant time delay in there, and we have more output measurements. We have a measurement vector here, and we have this control input vector. It's at the moment it's just basically one control input, and as usual, all these matrices of appropriate dimensions. The interesting problem that we like to do here is not just the stabilization problem, but we want to pick, let's say, pick an output measurement from this output measurement vector. And then we want to design a control law to track or to track the that output, that selected output is required to asymptotically track any constant step reference input. So if you can have a reference input like a step reference input, and or it can be a ramp type reference input. Now, this kind of problem is very commonly found in the process control, where we want to control maybe a certain variable and we wanted to track certain command reference input, like for example in power engineering and so on. And if you might recall that to achieve this, an integral controller is required if the system type is not a type 1 system. It's not classical control stuff. So we need to have some sort of like an integrator to ensure that the error, which is the difference between the reference signal and the output measurement yi, we had to go to 0. And so the idea there is, okay, we go into to define error, which is the difference between this command reference input and the output measurement that we wanted to track that reference input. And so we then introduce a stack variable, which is the derivative of it. In other words, this one is an integrator. When we integrate this e of t, we got this equation here, the derivative of xi, which is the error itself, is in terms of the reference signal and the output measurement yi of t. And so here ci is just a row, and that is the one associated with a particular output measurement that we wanted to track asymptotically any constant step reference input. Okay, so these are just classical problem in the literature. Now, if we augment this equation, which is a differential equation itself, together with the system itself, with the time delay system, then we arrive at an augmented system, which is this expanded system where we have a reference signal there. And these matrices, I, and all of that stuff, they have a higher dimension and they are defined according to the following. All right, so if we just concentrate on this particular system itself, then the idea of stabilization or output tracking is to find a feedback control law UT such that the system is stable. And so what happened in here is we define a control law of this particular form. Now, have a look at this particular control law. It is actually more general than what we normally find in the literature. In the literature, when we want to stabilize a stack feedback control law, when we find when we want to stabilize a control a time delay system using stack feedback, normally uh, we have this kind of stack feedback control law. Here we have this extra term in there. And the reason for having this extra term in here, it will basically significantly relax the stabilizability condition of finding a control law to stabilize the system. Okay, that's the whole idea behind that. And so if we then say, let find this feedback control law, let's find Fi and Fd, so that when we apply this one back into this open loop system, we get this closed loop feedback control system here. All right. And therefore, we want to find Fi and Fid. Okay, so we want to find Fi and Fid, Fi and Fd, sorry. And in other words, we augmented them. And then so basically, we want to ensure that this system here is stable. This problem is not a difficult problem. We can actually use LMI to find feedback controller Fi and FID. This adds additional freedom. This bit here adds additional freedom. And there is also, on top of that, we can even make this entire matrix goes to 0. In fact, we can even do that if and only if this rank condition holds. Okay, so what that means is that is the extra degree of freedom by employing this type of stack feedback control law into the system. All right, and if this condition holds, then we're going to get just a closed loop system without any delay in there. It's called a delay free. All right. In any house, if we don't have these conditions hold, then we can still do the stabilization. And of course, that stabilization problem is less conservative than this stabilization of problem of just finding Fi alone to stabilize the time delay system. Okay. And the good thing about this control law is that since we have developed the generalized functional observers to directly estimate this generalized functional, then it's a natural application to that. You can see that. So naturally, it just fit in very well. So if you find that in this chapter, we discuss two cases. The first one is we look at the time delay system where the output measurement vector does not contain a delay term associated with the stack vector. All right, so that's the first bit. And we want to realize this generalized functional observer for the system. And so naturally, what we do, we partition the feedback matrix Fi and Fd. So we split that into two bits. The first bit is the one that associated with the unmeasurable stack vector. And the other bit is associated with the integral variable, which is measurable. Okay, because when we look at xi, which is the integrator bit here, it is realized based on the difference between the reference and the output measurement, which is the reference signal and the output measurement signal. So this is a measurable variable. Okay. So the idea here is we split that into two bits, and then what we do is we realize this control law because this is not directly measurable. And that's why we use the generalized functional observers to estimate that directly. So that's the idea behind that. So we can do that. That's the good thing about it. And so what we do in here is we introduce a novel generalized functional observer to estimate that. And then what we did in here was just basically say, look, the observer that we come up with it just containing the available output measurement. And it's an observer with an internal delay. And the problem there is how do we find all of these parameters so that we can then ensure that this control estimation of the control law here asymptotically convert to the one that is based on the assumption that everything is available. Okay. So this is just like an idea of using an observer to estimate the unmeasurable stack vector and then incorporate that into the loop of with a controller, with a stack feedback controller. The thing about this scheme is that we do the generalized functional observer instead of just standard Lundberger or standard functional observer for time delay system. It's a generalized functional observer. Okay. And what we have in here is a schematic diagram of the control law. We call it observer-based control law, or we can call it a dynamic output feedback controller, whatever terms that we like to call it. Essentially, this is the block diagram of the time delay system itself. And then what we do is we take the output measurement vector, and from there, we pick one output measurement vector, the one that we really want to drive it to track the reference input. So that is the bit there. So we pick one output measurement yi of t, the one that we wanted to track this reference signal, and then we generate the error signal, and then we integrate it, and that's where we get this variable xi of t here. And then this is the control, integral control gain that fits associated with this ui of t there. Yeah. And so that where that bit is here. The other bit is the one that we really want to estimate it. We don't want to estimate it separately, like estimating a stack vector and then realize it. Instead, we estimate directly. And this is the implementation of it. You see that? Have a look at that. So we take the output measurement vector, come in here, delay it by 2 times, and then we get all these observer gains. And then we have this integrator in here. And then we realize this estimation of P directly. And then so this is the control law that we fit into the input of the system. And with this scheme, we will ensure that the output, which is this output here, will track asymptotically this reference command input. And this reference command input is a step reference command input, okay? Because we only introduce one integrator in here. And that only sufficiently to ensure the output measurement yi of t tracks this step reference command input. Okay, so that's the idea behind that. And it's, as you can see, it's the idea of estimating this generalized functional, which is this one, directly using generalized functional observer. And so what advantage of that we will discuss a little bit later. And as usual, we can follow the similar framework to realize existent conditions. So what we do is we then look at the error equation, and we want this error equation to be asymptotically stable. And therefore, we arrive at a number of equations, matrix equations. And when we solve them, it's just like what we did in the previous presentations. And then that's the idea behind that. Okay, so we want to show a numerical example for it. The reader can look into the derivation of the existing conditions and the underlying reason for ensuring the error goes to 0 based on these conditions in here. And so it's important to point out that in this scheme, we basically realize where we don't fit in any other control signal in there. So it's based on the available output measurement and delay output measurement. So we can call that this is a dynamic output feedback controller. We can call it that way if we want to. But essentially, it is the realization or the application of generalized functional observers to realize a generalized functional of a time delay system. Okay, and have a look at the scheme. It's basically fitting only the output measurement vector. So we got all the existing conditions, and we have a systematic way for realizing all of those parameters. And now here's an example. We just pick an example where just something along like this. And as you can see, we have one output measurement in this vector here, just one. And we want to drive that output. We want to make that output asymptotically track any step change in the reference input. We call it step change, okay? And then, so we then firstly realizing an augmented system. That's what we should do first. And by introducing an integral variable, we realize this augmented system. So we have an extra variable in our equation. And so all of these matrices, we can obtain them. And then based on that, we uh, design a feedback controller. Now, the good thing about this feedback controller is that we can actually get rid of all of these in the closed loop system. And this is because this matrix and this matrix, the rank is the same, which is the requirement. We stacked it in here. The requirement that we stacked it somewhere in here. Now, if this condition does not satisfy, it doesn't mean that we stuck there. We can still search for a feedback controller to stabilize the system for a given time. But in here, we pick this example just to show the generality, the advantage of employing feedback control law, where we got the delayed stack vector in that feedback control law. And in here, if we just employ that feedback control law, right, with FD in there, then we basically cancel out when we get the closed loop system, that becomes 0. And so we have a closed loop system, which is very stable. And it's independent of the delay. We can even assign the poles there and so on. All right. If we don't have this control term in there, then to stabilize the system, it's not very stable, or even sometimes we couldn't even achieve asymptotic stability for any given last time delay. So that's why we employ the generalized feedback control law. And that is already an advantage, as you can see. It's already an advantage itself. All right. And so when we go back into this numerical example, we realize that, look, it's good. We have this feedback control law where we got that term there and that term there. And then we split the control law into 2 bits that associate with the integrator. And this one is the one that contains unmeasurable stack variables. The unmeasurable stack variables are the second stack variable in the stack vector, because the output itself contains the first stack variable. The second stack variable is not available. So we can't realize this control law. We have to design a generalized functional observer. And this is in contrast to the current practice at the moment. What we can do at the moment without using generalized functional observer is basically estimate this stack vector and then delay it by tau and then realize in this control law. Okay, so we're going to compare with that later on. And then so we want to realize this generalized functional directly, and lucky for us, I mean, we could design um, a generalized functional observer, which is of this form. And the details we basically omitted in our work. We should leave it to the reader to verify our results. Okay, so we could find an observer, of this form to directly estimate the generalized functional, which is this control law in here. And not only that, it's actually an observer without an internal delay, So this is stable with tau equal to -2. And this control law itself is basically using the output measurement, the delay output measurement. Okay, so this is the control law for that. And when we look at the actual implementation of it, so when we want to realize this generalized functional observer, it's shown in here. And so we take the output measurement. This is just one. And then we delay it by tau. And then we have 1, 2, 3, 4, 5 proportional gains. That's what we call it. 5 proportional gains. That can be realized using like op-amp stuff like that if we do the hardware implementation. And we have a summer here and another summer here. So when we look at this, we have two summers. They can be realized using operational op-amps and one integrator. So this is the schematic diagram, hardware implementation of it. Right. And then keep that in mind. We then implement that feedback control law, and we also obtain simulation figures and all of that. And we actually did that for a delay of 5 seconds. And the figures here really show that what is going on. So at first, this figure show the trajectory of the output and the reference signal. The reference signal is the command reference signal, like step up and then step down and then step up. You can see that the output actually tracks this step command input there. And this figure 14 by 3 is basically the one without the observer, generalized functional observer. And then when we implement the generalized functional observer, we also superimpose on that the one with both control scheme, where the estimation and the other one is the one without estimation. So that's shown in these figures here. We can see that the dark line there really the one without an observer. The one with an observer, which is the generalized functional observer, exhibit a certain tension because the estimation there does not convert directly to zero. It take a bit of time. But then after that, you can see they all exhibit the same behavior. That tells that the control the estimation of the control law and the control law itself, they are same. So we have this kind of response there. Okay, so that seems so good so far. And then the other bit that we want to really show in this thing here, we say, let's look. another way to realize the generalized functional, which is the one we obtain from this expression in here, from here. Now, another way to realize it is to, you can see that there is an unmeasurable variable, which is x2 of t. And then another one is x2 t minus tau. So what if we design an observer to estimate x2 t, the unmeasurable variable? And that's exactly what we are saying here is we can also do that. It's no problem. For this example, we can do that. All right, we can do that. And so this is what we say here. We can here. This is the bit about the control law. It has this unmeasurable stack variable and the delay version of that unmeasurable stack variable. So if we can estimate x2, then this is another way that normally the one that is available in the literature at the moment is to estimate it and then delay it and then realize this feedback control law. So when you look at this feedback control law, it's actually different from the feedback control law that we realize directly in here. Okay, that's the distinct difference between the two of them. This is where we estimate directly. And this is where we say, okay, we estimate it by realizing an estimation of x2t and then delay it and then realizing it. Now, if we go ahead and design an observer to estimate this one only, it's actually also possible. It's also possible. And if we get it, it's actually the one shown in here. When you look at it, you say, oh, it looks simple, but bear in mind that even though it looks simple, when we actually realizing this control law in here, then the number of steps involved, we have that, and we also have to delay it and all of that. And so the actual implementation of this is shown in this block diagram here. Okay, this block diagram here. Have a look at this block diagram. To realize this estimation, we take the output measurement in and have a look at this bit in here. This bit itself is the realization of the estimation of x hat 2 of t, which is the estimation of the unmeasurable stack variable. So we got y of t come in and we sum it with omega t, which is exactly this bit here and this bit here. Okay. And then to realize this dynamics equation here, we got omega dot equal to minus, this is omega t here, and it's minus 2. We have to integrate it, and then we also have to add in that 2y of t or minus 2y of t in there. So this section here is the realization of x hat 2 of t. Now, the control law we have is realized based on this equation. So we get minus 9.5 times y and then minus 30 and all of that. So we have actually 4 terms in here. One proportional gain, another proportional gain, and a delay memory unit, another proportional gain, and another gain, and a delay unit. And that where it's shown in this block diagram. Okay. This output measurement here is delay. And then again, so this bit here realized in minus 30 yt minus tau. And that's exactly where you can see here, minus 30. And then, so you can see the rest of the implementation. Okay. the rest of that is we take yt in there, and then x we delay it. This is the bit we talk about. We got the estimation of the stack variable. We have to delay it, and then realize it with a proportional gain. So when we look at this all together, we have, as we summarize in here, we have one integrator, which is the same. Yeah, one integrator is the same. But we have three summers. Three summers. One, two, three. In contrast to the direct scheme, we have only two summers. And we have two delay units. What did we have in our previous scheme? In our previous scheme, we see that we have only one delay unit. We have only two summers. We have one integrator. We have one, two, three, four, five proportional gains. And with this new scheme, with this other scheme, we have one, two, three, four, five, six. Okay, we got six proportional gain. And as you can see, the way we realizing this control law two different ways resulted in two different schemes. This scheme is more expensive. Yeah, this scheme is more expensive. So if you are an engineer and you want to realizing some observer by control scheme, we always want to go for the cheapest, the less complex one. And it seems like the scheme that we propose based on generalized functional observer is simpler. Now, so that's the story behind that. On top of that, when we do the simulation of the implementation of the control law using this scheme here, we will see the following things happening. All right. So when we look at it, we see, oh, how come there is a spike here? There is a spike here associated with the one that using stack observe. Uh, the behavior of them after that is all exactly the same because asymptotically they all converge into the true control law. But in the initial stage of it, you can see that the red dotted line here is associated with the stack observer. There's a spike in there. And the explanation for that is because the observer scheme that we implement itself has this delay uh, estimation of the stack variable in there. So when we have it delay, the change in the error associated with the initial estimation, they then being delay and then it's exhibited in this expression. Okay, so that's the reason behind that. So when you look at the simulation, we have that initial changes. And that's what we meant in this presentation. We say that the outcome of using um, a generalized functional observer to directly realize a generalized functional result in a better, a similar observer by scheme. That basically the hardware components and also the computational aspect of it. And then it's better change in response is what we are referring to in this simulation figure. Okay, so you can see that, wow, it's good. It's good to use generalized functional observer directly. And then we can also, in the chapter, in this book, we also went further. We can say, look, we can even answer not only step input, we can answer a ramp type of input with zero steady state error. And so we introduce another integrator. And if we introduce another integrator, we have another variable. And this is just an abuse of notation. It's just that number two there means that we have two integrators. But the idea is clear from there. We introduce another integrator, and then we get the stack feedback control low, and then we split that into the one that's unmeasurable bit, and then we estimate. Then we estimate the unmeasurable control low directly using a generalized functional observer. Okay, so this is basically the scheme in there. We got with two integrators in there. And so we can see the simulation figure here now. Our scheme can also track RAM type signal, like it's a RAM up, RAM down, which also asymptotically tracks this kind of command input. Okay. And then this is just to show that without using double integrator, we exhibit, so we have a steady state error. And that's exactly what happened in the classical control bit. When we look at the steady state error analysis, if we don't have double integrators in there, and if the system is stable, but without double integrators, we have steady state error. And then we even went further. We said, look, we can even deal with the problem where the output measurements contain a delay term in there. And that's all consistent with what our development in the previous talks, where we say, look, we can design generalized functional observers to estimate generalized functional for output measurement of that form. So we even investigated this section also, and it's just basically we pick an example and we show that even with output measurement of that using the generalized functional observer, we can achieve that. Okay, and that's essentially this chapter is about an application. We have applied a unified framework for estimating the generalized functional to solve the problem of design dynamic output feedback controllers. And the way we do that here, we select an output, and then we want to drive that output to track a reference command input. And by estimating this control scheme directly, we have advantage of getting a similar observer by control scheme with fewer computational blocks and better transient response. Okay, so as you can see, we undertook an exploratory research into the design of generalized functional observers, and later on, we will then look at um, the problem of design in the next topic, where we're going to discuss the design of generalized functional observers to estimate a wider class of time delay systems. And that's all part of the book, where we show that the decomposition of the unknown input in time delay systems can give rise to uh, time delay systems which is which is unknown input free, but it contains multiple delays in there. So it's just like in this constraint here in section 5.4 of our chapter 5, we got this time delay system with multiple delays. And we want to realize this generalized functional here. Now, put that into perspective. At the time when we did this investigation, there was no methods available. And that's why in this book, we undertook a very detailed exploratory journey into finding out how we go about doing it. Okay, so thank you very much for watching. And I will see you again in the next presentation, where we will further explore in our journey to design generalized functional observers for time delay systems with multiple time delays. And that is based on the requirements that to asymptotically estimate an unknown input of a particular type of time delay system that gives rise to this kind of systems. Okay, so thank you very much, and I see you again next video. Bye for now.